compared to something like Y, because that's three-dimensional channels, and L is a set of parallel channels, though the size of the openings in cavity are not substantially different. But another way it probably is different is that it appears to be more basic. And this is not evidence for this, but it's an interpretation of this taken from a recent review article of Jules Bravo, where what is being looked at here is the calculated potential energy between the protonated form of the SiOAl and the deprotonated form. The deprotonated form is up here, and here's the protonated form as a function of the silicon-oxygen aluminum bond angle. And what one finds is that the potential, the energy it takes to deprotonate, to release the proton, is much higher if you have angles that are around 130 than it is if you spread that angle out towards 180. And then on top of that, I plotted the range of angles in three sets of zeolites, ZSM5, Y, and L. And as I was saying earlier today, it's really hard to interpret this, use this calculation to decide what the acidity of any of these zeolites are because of the range of angles you have. You only have, I think, 4 in the case of Y zeolite, but if you go over to the ZSM5, there's some 27 different silicon-oxygen aluminum bond angles. And so the question is, where's the aluminum and which of those are the acid sites that are accessible? And so which are the ones that I should put on this potential energy diagram to decide whether ZSM5 is acidic or not? In any case, the sort of feeling that the order of acidity ought to more or less go in this direction would be consistent with the idea that has developed that L zeolite, the thing that might be unique about L zeolite as a support is the fact that it is basic. And in fact, it was that idea that first caught my attention because we had been for some time looking at metal support interactions. We had particularly been interested in the rhodium on TiO2 system. And it seemed to me that the metal zeolite was possible, another example of metal oxide interaction, and it seemed to have some advantages over the others that we've been looking at, because the idea was that you could fill a pore with a particle, and therefore you might have a more uniform particle size, that if there was interaction between metal oxide, you could sort of encase the particle so that you would have a much larger fraction of the metal particle interacting with the oxides. So you might see bigger metal support interaction. And for a variety of reasons, I had thought that that would be an alternative explanation for why L was important in this hexane to benzene conversion. Now, and I say important because there was another thesis that was coming out of first at Exxon and then from Eric de Rooyen from Belgium, which was that it was primarily a geometric effect. Here's some one plot from Townsend and Steger work. What's being plotted here is what they call a selectivity parameter. It's the weight percent of benzene over benzene plus the cracking product C2 to C5 against what they call the terminal cracking index. The terminal cracking in hexane is the reactant. The terminal cracking index is the sum of the cracking products, hydrogenolysis products that are pentane, or the sum that are butane. It's some measure of the rate at which you just crack off the N carbons to make pentane versus cracking somewhere in between. Down here you have platinum on silica, and here you have a whole range of different potassium L zeolite supports. And there's no question that the selectivity goes up when this terminal cracking index goes up. But the question is it cause and effect, or are they just two effects that are parallel to each other? The idea that they had was that normal hexane sort of goes down these parallel channels and has a preferential end-on collision with the platinum, and then you get 1,6 rings collision. Now the problem with that is if you look at normal hexane and you look at its conformers, it could easily ball up and just move down the channel any way it wants. There's no reason why it should hit end-on. And so that doesn't look very convincing. Eric de Rooyen had another version of this, which he called it preorientation, and the sort of molecule sort of nest in the zeolite and starts to curl around on itself. That wasn't very convincing either. But we did look at this channeling effect, and we did it with another molecule where the conformation, we, in this case is an extended we, a former student of mine who's working on this project with me, was actually done in his laboratory, Daniel Nosco. The idea was that you choose a molecule where the conformation ought to be one that is sort of pretty well defined, i.e. methylcyclopentane. And now look at the selectivity between the possible hydrogenolysis products. It can crack here or here and go to hexane, or here and go to 3-methylpentane, or here and here and go to 2-methylpentane. And the idea would be that you expect a selectivity change when you conform it to go down the channel, because this one you might would have thought energetically would either approach the platinum particle blocking the pore, methyl end first, or this end first. And so the prediction would be if there's a geometric effect, you'll shift selectivity away from 2-methylpentane towards N-hexane or towards 3-methylpentane. And in fact, that more or less works. If you look at, these are results of platinum on silica, and I guess this is the 2-methylpentane, and this is hexane and 3-methyl, so the prediction would be if there's a geometric effect, you expect to increase the, say, hexane at the expense of 2-methylpentane. And in fact, something like that actually happens. When you go to the L-zeolite, you do see a shift towards the N-hexane and 3-methylpentane at the expense of 2-methylpentane. So it does seem to me that there is some component, there may be some component of this geometric effect here, but I don't think it's the primary one that's involved in causing the normal hexane to benzene reaction. Now, another thing that I can say before I get around to talking about the details of what we tried to do is that after all this work, well, you're probably quite aware that a lot of effort is going on in this area now, right? The first people on the bandwagon was Chevron, and then along came Exxon that I don't know what their current count is, but I did a literature search a few months ago, and they had 32 patents in this area. UOP is active, and probably several other people that I don't know. But Chevron got several patents. And one would ask, given all that Bernard did and the way they patented and published it, what did Chevron add? Well, what Chevron did add, I guess, was an elaboration on this question of non-acidity and how you could make the support even more non-acidic. And their measure of non-acidity was the absorption of pyridine. And here, as a function, and changing the cation from potassium to these alkaline earths, and here's the acidity when you calcine at low temperature: magnesium, calcium, strontium, and barium. And then if you calcine at 866 and exchange with barium, there is, by pyridine absorption, no measurable acidity. Why is that? Because if you put alkaline earths in most zeolites, they may neutralize the acidity of the anion host, but then they hydrolyze water and they add a proton back and they create acidity. Well, if you look at the structure, what's happening is that there are these normal channels, but then there are these small lock cages off the main root, as it were, cancrinite cages. And in fact, when you calcine at this higher temperature, the barium moves into these lock cages. So it may well hydrolyze water and make protons, but it puts them either there's not room to get the hydrocarbon in there, or they're not accessible. In other words, it doesn't put the protons along the channel where you can get a pyridine, and so that's probably the reason it's non-acidic. So that was Chevron's, I guess, basis for their patent. It certainly was maybe not a sufficient to our understanding that you could make it even less acid, make even more bases, and in fact, it does make a better catalyst. Another point to be made is that what this catalyst is really good at is normal hexane to benzene. This is the relative aromatic reduction as a function of carbon number. And its selectivity relative to conventional platinum rhenium sulfide treated in the proper way, one must assume, since Chevron did this, it falls off as you go to higher carbon points. So what's really unique about it is hexane to benzene. It sort of loses its uniqueness when you go to higher hydrocarbons.